Okay, when we're not dealing with binary compounds, for the most part we will be dealing with compounds that are ionic and contain polyatomic ions. That is, ions that are themselves contain covalent bonds that hold the atoms of the ion together, but there's a net charge on the ion that is distributed throughout all of the atoms. And so many of these ions we don't need to memorize. You will have a table or have some other resource to indicate the name and the formula and the charge, but there will be a handful that you will be responsible to memorize. Okay, so polyatomic compounds contain at least one polyatomic ion. And before we talk about the rules for naming these, I want to introduce some of the common polyatomic ions. So there's only one positively charged polyatomic that we need to be concerned with, and that is the ammonium ion, NH4+. Now in this table, I've indicated in these red boxes the ions that I expect you to memorize. So you should know that ammonium is NH4+. You need to know both the name and the formula and charge. So in addition to ammonium, we want to know a number of oxyanions. So we have the nitrate is NO3 minus, sulfate is SO4 2 minus. Let's take that. Let's see, let's get rid of that box there and write it a little bit better. So the sulfate ion, SO4 2 minus, the hydroxide ion, OH minus, the phosphate ion, PO4 3 minus, carbonate is CO3 2 minus, and chlorate is ClO 3 minus. Now we'll talk about some of the trends that we want to start to identify with these ions, but for now you should certainly work to make sure that you can identify the name, charge, and formula for this handful of polyatomics. Now when we name polyatomic ion containing compounds, we're really going to use the rules for our binary compounds, only now instead of having a binary, we will also be naming this polyatomic ion containing compound. So for example, we can take the sulfate ion and bring it and form a compound with sodium. Since sulfate is a 2 minus charge, SO4 2 minus, we will need 2 sodium ions to balance the charge. And so Na2SO4 we simply name sodium sulfate. Again, the cation followed by the anion in all cases, just as we write the formula. We could have a similar compound, Na2SO3, and this differs only in one oxygen, and this SO3 2 minus is called the sulfate, and so we simply name this sodium sulfate. Similarly, we could have calcium phosphate. Phosphate has a 3 minus charge. Calcium, being a group 2 metal, has a +2 charge, and so we would need to bring these together in a 3:2 ratio. Notice here that the phosphate group is in parentheses with a subscript 2 outside the parentheses. This indicates that there are 2 phosphate ions within the formula unit of this compound, or 2 moles of phosphate for every 1 mole of calcium phosphate. So when we're dealing with type 1 metals with these polyatomics, we simply name the cation and then the anion. For type 2 metals, like iron, we stick to our rules for type 2 metals, right? So here is Fe3PO42. Again, we have a 3:2 ratio here, okay? Since phosphate is a 3 minus charge, and there are 2 of them, and there are 3 irons in this case, so that means each iron has a +2 charge. And so in our systematic name, we will call this iron 2 phosphate, or in our classical system, we would call this ferrous phosphate. Okay, so we're going to really stick to the same rules we've been using all along. Okay, now in these polyatomic ions, most of these ions are what we call oxyanions. That is, they contain oxygen. And there's a number of trends that we're going to want to identify. First, let's look at nitrate and nitrite, right? they differ in this ate versus ite designation. And the difference between these two ions is the number of oxygen atoms. Okay, so both of them have a -1 charge, and we name the one with the larger number of oxygens, NO3-, we call this nitrate. So that ATE ending indicates that there are more oxygens, and the ITE ending indicates that there are fewer oxygens. Okay, and we'll see a few more examples of this in just a moment. Another trend that we might notice in some of these is that similar oxyanions form within a given group. So chlorine and bromine are both halogens. They tend to have similar chemistry based on their similar electronic structure, and they both form an oxide with 3 oxygens and a 1- charge. And we name them the same, chlorate and bromate. So they both get the ATE ending. They both have the same number of oxygens and the same charge. And this is a trend that's fairly common. Another common trend that we see with these oxyanions is we can undergo a protonation event. That is, we can add an H+ ion to one of these oxyanions, reducing the negative charge by 1 when we do so. So carbonate with a CO3 2- charge, when we protonate that is when we add an H+ ion to it, it becomes HCO3 with a 1- charge. And we name this hydrogen carbonate. And so this hydrogen simply indicates that we've got a protonated carbonate ion. Commonly, this particular ion is called bicarbonate. And we'll see this with many of the oxyanions. We can add an H+ ion to them and call them hydrogen carbonate or hydrogen sulfate or hydrogen phosphate, etc. So again, with these oxyanions, we see this ate-ite designation. Well, and these are sort of, let's see if we can move these over a little bit. Okay, so we have nitrate with 3 oxygens and nitrite with 2 oxygens. Both have the same charge. Similarly, phosphate with 4 and a 3- charge, and phosphite has 3 oxygens but also a 3- charge. So this is true for most of the members of a given trend. Now, chlorine oxides are really a unique series, because instead of just having 2 as in nitrate, nitrite, phosphate, phosphite, etc., there are actually 4 common oxyanions of chlorine. So there is ClO-, ClO2-, ClO3-, and ClO4-. They all have a -1 charge, but we need to name these ions in such a way that we can distinguish between them. So first of all, we pick the middle two. The ClO2- we call chlorite with fewer oxygens, and ClO3- we call chlorate with more oxygens. So then if we add another oxygen to chlorate, we get perchlorate. So that per means there's even more oxygens than the chlorate. And then we go down from chlorite, ClO2 with a 1- charge. If we remove 1 oxygen from that, we have hypochlorite, meaning fewer oxygens than chlorite. And notice again, it still has that 1- charge. Okay, so when we combine these polyatomic ions with different metals or different cations, we use the same rules that we have identifying the type of metal, and in forming the compound we just need to be aware of the formula and the charge of the ion, and then we name the ion just as it's named.